So now we are going to study some properties of wave function with respect to time. Okay. So remember Schrodinger time dependent equation I h bar del psi by del t, and notice now I write x comma t. So I won't write it everywhere because it will look like very bad. So I note now I am using x comma t because we are evaluating with respect to time also now, right? Okay, is equal to negative h bar square by 2m del 2 psi by del x square plus Vx psi. Notice in case of quantum mechanics, we assume potential and potential difference same. There's a chance that I say that it has potential. I say sometimes it has potential energy. So don't get confused. Just assume it is the potential energy only, right? Okay. So let's do something over here. Minus h bar square by 2m del 2 by del x square plus v of x. Bring the psi outside. Yeah. Okay. And now this thing is called this is called Hamilton operator. Hamilton operator, right? Hamiltonian operator, right? It is said like this, and it is represented as h. So you get h applied on psi is equal to I h bar del psi by del t, right? It is del t. Okay. This is another way to write Schrodinger time dependent equation, right? I hope you are understanding this. And now this is what? This is h applied on x comma t is equal to I h bar del x comma t psi by del t, right? So now let's find a basis vector over here. I mean the eigenfunction using phi, which is only dependent upon space, is equal to some eigenvalue. It is the energy or the eigenvalue in this case, phi of x. This is the case. Okay, I hope you're understanding this. This is your eigenfunction, this is your eigenvalue, and in this case it is also energy. And since Hamiltonian is a energy operator basically, right? So you get h applied on phi is equal to E applied to phi, E multiplied by phi basically, sorry. So now what we are going to do, let's see, we'll find a wave function using this. Let's see how we will evaluate this psi. We'll solve Schrodinger equation for it. Let's see how we get what we get. Let me erase this. So now we can write psi of x comma t is equal to summation as I, whatever the value is going from. It is like infinite values. So it is ci, and you use the ket symbol dependent upon x, right? Notice it is independent upon time. It is independent of time, which means the coefficient, it must be time dependent, right? So how we are going to solve this? Let's see. We have h of psi of t, okay, is equal to the summation I from ci h of phi I, right? Like this. Basically you applied Hamiltonian operator on both sides basically. Okay, so you got, what is this quantity? Well, I and this ci, and this was equal to ei into the state of phi I. Is it okay to understand? Okay, so now what we are going to do, and yeah, this is equal to I h bar del by del t of psi. I'm not writing t right now, but you know that it is this quantity. Okay, and now notice that you can write this expression I c I e I states of phi I So in this we have got I h bar del by del t of the summation I ci of this states, and then you just apply this ci e I pi I. This is equal to, since it is independent of the x, so you get I h bar summation I del ci by del t. Since it is only dependent, well, leave whole multiplied by pi I, right? You got this thing. So notice from this, if you know, if ai vector plus bj vector plus ck vector is equal to some di vector plus ej vector plus fk vector, then this must be equal to this and this must be equal to this. I mean, a is equal to d, b is equal to e, and c is equal to f, which means that the corresponding components are equal, which means since this is also the, since these are the basis vector and these are also the basis vector, so the corresponding basis vector must be equal, which means c is I ci ei must be equal to I h bar, this is square root of I, remember, okay, is equal to the del ci by del t, right? I hope you are understanding this, okay. So just solve this now. ei negative I by h bar, this is square root of I, remember it, is equal into dt is equal to dci by d divided by ci, since it is only dependent upon the time, so that is why I was going to say there, but I said that I will tell later, okay. So you will integrate it from 0 to t, and this c at I when it is equal to 0 and c at I at time t, right? You are evaluating this. Let me raise this. So now let's see what we get. I negative I e I by h bar into t is equal to the ln ci at t by ci at 0, which means ci at t is equal to ci naught e to the power minus I by h bar into EIT, right? Let me change the marker. I hope its ink is over. Okay, so this is how you calculate the coefficients, and now when you calculate the psi at x comma 0 means at time is equal to 0 is equal to summation as I goes from whatever value c of I0 and the states of phi I, states of whatever quantity which we are calculating, psi of t will be equal to the summation of I from I as c of I at t into the states is equal to the summation I ci at 0 e to the power minus I by h bar into EIT pi I, this thing, okay. And this is how you evaluate it, okay. And if it is a continuous function, then in that case we write psi of t is equal to negative infinity to infinity c of some lambda comma 0, where lambda is some arbitrary value, e to the power negative I by h bar et phi I x d lambda, and this is how you evaluate it, right? Okay, so let me erase all this, and then we will and this tells that how the wave function varies with respect to time, right? And to a surprising thing, that if the wave function is made up of the eigenfunctions itself, then in that case the all other physical quantities, for example momentum, position and everything, they all will remain same, they won't change with time, and it is something really amazing to know. But if the wave function is not made up of the basis vectors or the eigenfunctions, in that case the other physical quantities, they will not have a fixed value, but their probabilities will still remain the same. We have to, so this is a nice fact which I have told. And after all this, you should know that the wave velocity is equal to the group velocity by 2. This is something from the SHM also, and in the quantum mechanics we can also prove it, right? But we won't discuss it right now because it's nothing to do much. Okay, and yeah, remember one thing: if there is a operator, suppose A, and it is and in a commutator, and if A with H is equal to 0 in this case, so we say that A is constant of motion. This is the basic thing which I told over here, that the physical quantities may not change with respect to time. This is the quantities which are commutative with the Hamiltonian operator are constants of motion, which means they will not change with time, right? And sometimes it is referred to as stationary states also sometimes, right? Such states, okay? And there's something called a bound state potential. And what is a bound state potential? Basically, when the particle is bounded in a region. For example, now we are coming to the 1D box problem, or the deep square well potential or infinite square well potential. Everything means the same. And in this case, the particle will be bounded, and we will do some numericals on that and the derivation part also. And then we will end the lecture on a happy note, obviously, because we completed something really vast topic in a one shot, in a one go. And it is like it did not seem possible when I started, but I felt, yeah, I will be able to do this. And yeah, there are many other topics which needed to be covered, which I may cover later, because obviously I covered this in one shot. I might cover the other portions of the quantum mechanics which are more sort of high level things in the next one shot, because this is for the beginners, and like it is for the people who have great interest in the quantum mechanics. So that is why I started making the one shot, right? So now, keeping all that aside, and let's dive into something called bound state potential. If I have space, I can just explain it right now. What is it all about? Suppose if you are saying I'm taking this example of the classical mechanics, that spring system, suppose its potential is equal to half kx square, right? And suppose it's represented by this, right? This is its total energy, E. At this point, it will have some potential energy and the rest will be kinetic energy. Here it will have its maximum potential energy, but zero velocity, and it will just move like this. It will be bounded between these points, and the other regions are forbidden. It can't go like that. The spring can't go beyond that thing. It can't go something beyond its potential. So such things are called bound state potential, right? Okay. So we will discuss now 1D box problem. Okay. Let me raise this, then we will start. So now we are going to start with the deep square well potential, or 1D box problem. So remember that we had confined our course to the 1D system only, 1D particle system. So that is why we are dealing with the 1D box problem first of all, and then we will discuss other problems too in my. So in my later one shots, I may cover 3D quantum mechanics also, and other things if we get time, that barrier tunneling effects and many other things, tunneling diodes and many other problems. But right now we will be able to discuss only this and its problems. And okay, let's start. Okay, so suppose there is a particle which is bounded from x is equal to 0 to x is equal to L. The potential is equal to 0. But before that, means for values x less than the potential, x less than 0, the potential is infinite, and for x greater than L, the potential is still infinite. So how do we interpret this? Well, what does it has to tell? it is telling that the particle is bounded between this region only. It has tell this, which means potential is equal to 0 for x between this and is infinite for x less than 0 and x greater than L. Okay, so now let's apply Schrodinger time independent equation, because there's nothing to do with the time over here. So we are going to apply negative h bar square by 2 m del 2 phi. Phi is the again the eigenfunction. Del x square is equal to e phi. Why so? For x between these quantities, right? And of course, if it is greater than 0 for x greater than 0 and for x less than 0 and for x greater than L, in that case what we will get is that in that case we will have a term vx into phi, right? This plus v of x into phi, we will have that also. But in that case, since v of x is becoming infinite, so in that case we know that phi is becoming 0. So the wave function is 0 all over, means all over except this space, this region from 0 to L. So we need to create such a wave functions which must have this property that it is continuous. The wave function must be continuous, it must be finite, and it must be square integrable, which means it should be realistic wave function integrable, right? So we have to keep these things in mind before forming the wave function. So for that we are using the eigen functions and then we will evaluate it further. Okay. This is simply the Hamiltonian operator, and okay, forget this and let's start. So basically you get del 2 phi by del x square is equal to negative 2 me by h bar square into phi, and you can say this as k square just for the time. This can be said as a k square, which means d del 2 phi by del x square, or basically since it is a position dependent only, so you can say it like this. This is equal to negative k square phi. And if you compare it from the SHM equation, the equation is of course same. We of course distinguish classical and quantum mechanics a lot, but the equation will be solved mathematically the same. So this is like SHM equation only. So you get a solution of the phi. You get phi is equal to a cos kx plus b sine kx, right? Or you can write it like this, over here sine, that is better, into cos, like this. You will write it like this. So there is a solution to this equation, right? Of course you know this. A bit of classical mechanics you should know for this, and if you don't know, I will try to make a one shot on classical mechanics completely. But for the time we have to do it on your own, okay? Because already the one shot has gone like very big. So just try to understand that this similar to SHM wave equation, and from that we get this. Okay, let me raise this, then we will move further. So now we know that phi is equal to a sine kx plus b cos kx, right? And you remember k was equal to k square was your 2 me by h bar square, right? So now you have to understand one thing. Phi at 0 will be equal to 0, right? This particle cannot go on that barrier, right? So it is equal to a sine of 0 is 0, so you get 0, and this is equal to b, which means b is equal to 0. So you already eliminated one term from it. Okay, so you got phi is equal to a sine of kx. Since you are trying to make a general function, the wave function, this is the eigenfunctions which we are trying to deal with. So now what you are going to do is that you will evaluate at L, and notice that at L also the probability to find the particle is 0. So it is equal to 0 and it is equal to a sine kx, right? KL. But notice that KL, that A can't be 0, right? K is a constant, it is not 0. L is also positive, it is also not 0. Which means then what is becoming 0? The sign of KL is becoming 0. And of course, KL, the product is not become 0, which means they must be integral multiple of pi. The positive integral multiples. KL, KL is equal to n pi for n positive integers, right? So you get the value of k as n pi by L. You substitute it over here and you get phi of x is equal to a into sine of n pi by L into x, right? And you got a eigenfunction for this, right? And from this, and since it is for the n, is right, these are the eigenvalues, right? And from this you can find phi 1 of x a sine n uh, pi x by L. For n is equal to, you will get 2 pi into x by L, and so on and so forth. And you can calculate the first energy also, the ground energy of this system, and you will get it as h bar square by 2m, and you will get h bar square by 2m. What is the value of k? K is equal to n pi by L, so you get n pi n square, this, right? You will get this. And when you plot this wave function, this eigenfunction, what you get? You get like this. In this case you will get it like this, okay? Since it is going from here to here, and from pi by 2 it is going downwards, okay, between 0 to L. In the case of phi 2 of x, it is becoming a sine of 2 pi x by L, and in that case you will get somewhat like this. This is your L by 2. You plot this, since at L by 2 it is becoming 0, and after that it is going, okay? So now let's see if something is left. Yeah, one thing is left, that we need to normalize the function. So in that case, for the first one, if you normalize, you know the method to normalize this. And if you normalize, you get mod a square is equal to 2 by L. So you, from this you can get many results for a, but if you choose one, you will get root 2 by L. So you can substitute root 2 by L in this case, okay? Right. So now let's move to some next concepts. Okay, so we have completed the derivation part, and now we are coming to the problem solving. Okay, now let's start with the problem solving. So now let's start with some problems. So question 1, it states that a particle of mass m in an infinite square well, it is that only 1D box, infinite square well, well potential obviously, from 0 to L has a wave function psi of x is equal to root 30 x into L minus x divided by L by this quantity. Then find probability, that find the probability of finding energy, the finding energy to be h bar square pi square by 2 ml square. And basically, if you note that this is the energy, this is the energy when you substitute n is equal to 1. If you remember, we calculated it right back there, n is equal to 1, right? Okay, and notice that this is not a eigenfunction itself, so it will represent the properties. So when we solve this, we get psi of x is equal to the summation I ci pi I of x, we get this, or we can represent it like this, the psi of x is equal to summation ci pi I, right, like this, where phi is the eigenfunctions which we had calculated, right? So basically we are trying to find ci is equal to c1. So basically we are trying to find the c1 because we have to find the corresponding phi 1. So we are trying to find the probability of energy in this region, right? So notice that how do we find ci? I mean c1, it is equal to integral negative infinity to infinity of phi of x as it is, phi of x into the conjugate of phi 1 of x dx, right? You know this. So from this, if you substitute negative infinity to infinity, psi of x, we are given that into this is equal to sine of pi l by x dx. Sorry, this is pi x by l, and there was a constant which you had calculated root 2 by l, right? In this case, if you remember this expression, right, we had calculated, and since it is the real value only, so the conjugate will still give the same value, right? So we will solve this thing. You substitute psi of x over here, this, and then it's pure mathematics, the integral part, and you will end up getting c1 is equal to root 960 by pi cube. And for the probability, if you remember, we calculate c1 mod square, which is equal to 960 by pi to the power 6, which is equal to 0.94. So the probability to find this energy in this wave function using this wave function is this 94%, which means the graph of R looked like this. So we expect this to look somewhat like this, somewhat very close to maybe like this. This is for psi of x because it is very much close to this, but still there's 6% chance that you don't get this energy. It means that this is not a eigenfunction, but still it gave a nice precision. But and it also tells that it is not an eigenfunction itself, because if it was an eigenfunction, the probability must have been 1 to find that, right? And in this case, when you will evaluate the quantities, the physical quantities, you will find that the values are changing with respect to time. The energy will also change with respect to the time, but the probability to find that thing will never change, right? But if it was a eigenfunction itself, then the probability must have been 1, and the constant and the physical quantities must have been unchanged with respect to time. But in this case, it is not eigenfunction, so that's why the things will change, but the probabilities will remain constant, and that is the beauty of quantum mechanics. Okay, so now let's see if we have another problem, and then if we don't have, then we will end the lecture. Okay, so we have one more problem. We'll do this and then we will end the lecture. So now let's see the second problem and then we will wind up. The question states the wave function of a particle in a deep square well potential from x is equal to 0, from x is equal to L at t is equal to 0 is given by psi of x is equal to 1 by root 5 into the quantity phi 1 of x plus 2 phi 2 of x, this quantity. And in this we are going to study something really interesting about the bra and the ket symbol in this, because there are some operations which will be done using that. So You have to be very much concentrated towards this thing. Okay. So phi 1 and phi 2 are the energy eigenfunctions corresponding to the ground state and the excited states, right, respectively. So we have to find the wave function at t is equal to the time is equal to ml square by pi h bar. Okay. So first of all, let's see how the function may look. Of course, let's see. Phi 1 will look something like this, and phi 2 looks like this. Okay, so you are adding this. So in the first case, it looks like this with something like this, and in this you will minus. So the final graph which you will expect to get is this. This is your wave function actually. This is your given wave function at t is equal to 0, right? Okay, and it will change with time. Of course, it will decrease, increase, then it will decrease, then increase over here, and so on and so forth, right? Okay, so let's see. Yeah, let me raise this. I hope you all must be knowing the question. Now we are solving the first part, and in that case we know that psi of x comma 0 is equal to summation I c I phi I of x, right? Okay, and psi x comma t, this ci at 0, and when you apply at time t, it will be at 0 e to the power negative I by h bar into the quantity e I t pi I of x. Remember, we had calculated this thing. Okay, this will be ci at t, and ci at t we had calculated this thing. Okay, if you remember that. Okay, so now you remember that psi of x comma 0 is equal to 1 upon root 5 phi 1 of x plus 2 by root 5 phi 2 of x. So psi at x comma t is equal to 1 by root 5 1 x into e to the power negative I by h bar into e1 of t plus 1 by root 5 phi 2 of x into e to the power negative I by h bar e2 t, right? And you all know that e1 is equal to, from the eigen values which we calculated, like we had calculated now, that en is equal to that we had assumed that k square is equal to 2 me by h bar, so we got en is equal to h bar by 2 m h bar square into k square as n pi by l whole square. We had got this now. So e1 when you substitute 1, and e2 when you substitute 2, and so on and so forth. You can watch that 1D part, that 1D box problem. In that we had calculated the eigenvalues. So this is e1 and this is e2 over here. And now when you evaluate this at given time intervals, at the given time, you will end up getting psi of x comma t, and this is your work to solve this. You will get to phi 2 at x minus phi 1 of x, right? When you evaluate further completely, you will end up getting this, which means your wave function has changed, but the probability of energies and everything have remained still the same. That's the beauty of quantum mechanics. Okay, now the second part is something interesting which we will discuss, but first I have to get some space. So now let's see the second part, and it states that you need to find the expected value at t is equal to 0. Okay, so expected value at x is equal to this quantity I have told before, and you remember that ket of psi is equal to 1 by root 5 of the states. We are just accumulating all the states, this state, these two states, and then you're finding the brass symbol in with respect to psi over here, and this, And notice when you apply the bra symbol over here, then in that case, if there's any complex, if it would be a complex function, then you would have taken the conjugate, okay? But since it is a real, so we don't need to worry. This is bra psi phi 1 plus 2 bra phi 2. This, you get this thing, okay? So now let's evaluate the things, okay? Let's see. So basically you get this operator over here, x. This is a position operator which you are applying. So it is 1 by root 5 whole square. Of course, since you are using the properties over here, and it is equal to the bra phi 1 plus 2 bra phi 2 multiplied by x ket phi 1 plus 2x applied on phi 2, right? You get this thing. And just as in normal calculations you do, just multiply it, you get this, just like in the normal calculations you do. 2 times phi 1 this x and this is phi 2 plus 2 phi 2 x phi 1 plus 2x plus 2 plus 4 phi 2 over here, x over here, and phi 2 over here, okay. And notice that over here we have done that this is the expectation value of x if the wave function was psi 1, and over here also. So notice that the wave function for phi 1, it is very much symmetric from 0 to L. So we expect the value to be at L by 2. And in the case of this, it looks like this. And when you square it, it will be like this. So again, the expectation value will be at L by 2. So for both the case, you will get L by 2 and this 4 into L by 2 plus, and notice that in this case there is no complex function over here, which means that they both are equal since they are real, okay? Plus 4 times this quantity, okay. And how do we evaluate it? Let's see. Well, it's again the calculation part, that negative infinity to infinity of the quantity root 2 by L into sine of pi x by L pi x dot root 2 by L into sine 2 pi by L into x into dx. You evaluate it, and it's your work to evaluate over here, because if I evaluate it will take lots of time, and it's simple, just mathematics. It's your mathematical skills which you will save you over here. So you have to evaluate this, and you will end up getting minus 16 L by 9 pi square, right? You will get this. So you get 1 by 5 into 5 L by 2 minus 16 L by 9 pi square, and L by 2 minus these quantities. When you solve, you will get whatever result. This is the final answer which you will get. Okay? I hope you are understanding how we have calculated, and since it is a multiplier of 4 also, so you get L by 2, this 4 minus 64 by 45 L pi cube pi square into L, and this is the probability at t is equal to 0, right? So with this we come to an end to our one shot, and I hope that you all really liked the video and understood something new over here, learned something new. So please do like and subscribe my channel, and please support this video as much as you can, and take care. Bye bye.